Generative voice models reliably synthesize high-fidelity speech for short, isolated utterances, but when tasked with generating coherent, multi-speaker conversations, the architecture typically fails after a few minutes, losing track of voices, tone, and pacing. This barrier represents the standard limit of short-form synthesis, a boundary that traditionally restricts generative models to lengths measured in seconds. Microsoft Research has now introduced VibeVoice, a novel framework designed to extend this capability to 90 continuous minutes of audio, managing up to 4 distinct speakers in a single generation pass. This chart graphs maximum speech length. While leading systems cluster near the bottom, VibeVoice spikes past 5,000 seconds. And as the inset shows, this length doesn't degrade performance. VibeVoice 7B beats Gemini and ElevenLabs in human evaluations for realism, richness, and preference. Solving the context length bottleneck without a drop in audio quality allows developers to move beyond generating short social media clips, enabling the creation of feature-length, multi-participant podcasts in a single prompt. To understand how VibeVoice achieved this duration, we have to look at why auto-regressive generation over long context windows exhausts large language models. Traditional text-to-speech models rely on discrete audio codecs, like encodec or DAC. These systems translate continuous sound waves into a finite vocabulary of discrete tokens. When an LLM processes these discrete audio tokens at standard rates of 50 to 600 Hz, its memory fills rapidly. The system hits a solid wall of context limits after only a few minutes of audio. To bypass this limitation and create longer outputs, previous systems synthesized hundreds of short, isolated audio clips and manually stitched them together. This concatenation process destroys the flow of a conversation. It breaks natural turn-taking, strips away global context, and ruins consistent pacing between speakers. Achieving true conversational realism requires fitting the entire unbroken audio history inside a single context window. The model needs to remember the tone and rhythm from 20 minutes ago to inform how a speaker responds right now. This underlying sequence inefficiency in discrete audio tokenization creates a much stricter limit on generation length than raw compute power. VibeVoice solves this sequence inefficiency by abandoning high frame rate discrete tokens entirely. Instead, it relies on a continuous acoustic tokenizer. This entirely new tokenizer takes complex, high-frequency audio data and compresses it into a highly dense, continuous state. The system uses a continuous sigma Vea encoder. It processes raw 24 kHz audio through 7 stages of causal convolutions, designed specifically for efficient streaming. This hierarchical architecture downsamples the original audio by a factor of 3,200. Standard codecs operate between 300 and 600 frames per second. VibeVoice drops this to an ultra-low 7.5 frames per second. This aggressive compression creates a roughly 2-to-1 ratio between audio and text data. 2 acoustic tokens take up almost exactly the same sequence length as one standard text token. By aligning these rates, the LLM reads audio data at nearly the same sequence density as a written transcript. Because the sequence density is so highly optimized, an LLM can natively process an hour and a half of audio inside a standard 64K context window without crashing. Compressing the audio is only the first step. VibeVoice also streamlines how this data is fed into the core LLM, entirely removing the need for complex, separate prior networks. The input prompt is constructed by taking continuous voice latent features and simply concatenating them directly with the text script. These audio and text tokens are interleaved step by step and explicitly tagged with identifiers, tracking exactly which speaker is active at any given moment. This creates a single, unified hybrid sequence, Speaker 1's voice and text, followed by Speaker 2's voice and text, fed straight into the sequence model. The LLM processes this entire chain and outputs a hidden state for each specific token step. Because VibeVoice uses a pre-trained Qwen 2.5 LLM as its core, it treats this complex hybrid array exactly like a standard text prompt. Treating continuous audio and discrete text as an interleaved sequence allows the system to track conversational awareness over long durations. This introduces a distinct new architectural problem. If the compressed audio tokens are continuous distributions, a standard LLM cannot easily predict the next token in the sequence. Standard LLMs rely on softmax classification. They are designed to predict probabilities over a finite, discrete vocabulary of words. When you force a discrete classification system to sort this continuous fluid data, the mathematical process breaks down. VibeVoice resolves this incompatibility by employing token-level diffusion. Instead of forcing the LLM to predict the exact audio token directly, the LLM's output hidden state acts as a conditioning signal. It guides a completely separate diffusion model. This specialized diffusion head is a lightweight 4-layer network that operates on every single token step during generation. During inference, the diffusion head takes a block of random Gaussian noise and refines it through an iterative loop, gradually removing the noise to reveal a clean, smooth acoustic feature. The hidden state provided by the LLM acts as the blueprint, telling the diffusion head exactly how to shape that static into the correct sound. This generation process requires only 10 denoising steps, utilizing an efficient solver and classifier-free guidance to maintain high processing speeds. Next token diffusion links the long-term autoregressive reasoning of a large language model with the precise high-fidelity synthesis of a continuous diffusion network. Operating at 7.5 frames per second invites skepticism. In traditional signal processing, compressing an audio waveform that aggressively should result in severely degraded robotic speech. To test if the acoustic quality survived the compression, engineers measured the reconstructed audio using PESC and UTMOS, standard objective metrics for speech quality. This chart details audio reconstruction metrics across different tokenizers. Discrete codecs operating between 300 and 600 Hz sit next to VibeVoice's acoustic tokenizer, running at just 7.5 Hz. Despite operating at a fraction of the frame rate, the continuous tokenizer achieves higher reconstruction quality, logging TESC scores over 3.0 and UTMOS scores over 4.1 on clean test data. The continuous Sigma VA architecture preserves essential acoustic variance far better than discrete quantization at equivalent sequence lengths. Extreme compression only serves a purpose if the model fully retains the perceptual, natural qualities of the human voice. The data proves it does. Moving from the tokenizer to the complete system, the end-to-end performance of the trained VibeVoice model was benchmarked against the current leading platforms. Objective transcription accuracy was measured using word error rate, evaluating how perfectly the generated audio aligns with the requested text script. This bar chart displays the whisper word error rate for long conversational generation. VibeVoice 7B achieves a score of 1.29, recording fewer transcription errors than Gemini 2.5 Pro at 1.73 and 11 Labs V3 Alpha at 2.39. Researchers noted that scaling the core LLM up from 1.5 billion parameters to 7 billion parameters yielded heavy performance gains across all measured objective metrics. The larger model demonstrated richer timbre, tighter natural intonation, and superior zero-shot transfer capabilities when handling cross-lingual applications. Furthermore, while the architecture is explicitly built for 90-minute podcasts, it maintains robust generalization and low error rates on standard short-utterance benchmarks. Transitioning from high frame rate discrete codecs to next token continuous diffusion allows text-to-speech models to scale while maintaining long-term context. Native feature-length audio generation provides the structural foundation required to run continuous, deeply conversational AI agents.